So we're going to talk about the introduction to chemical bonding, valence electrons, the ionic bonding. I'm really not going to talk about Coulomb's law. I want to jump over that portion. So to go on, we have introduction. First of all, a chemical bond is a force that holds atoms together. Why do atoms bond? Well, they have one reason only. Is really they not run only, but the main reason is they want to become stable. Remember, the overall stability has become like a noble gas. That's the key in this process. There are two forces they're dealing with, though. They have the force of attraction, the opposite charge attracting, but they also have repulsion because they have electrons pushing each other away. The three types of bond, you have the ionic, transferring, covalent sharing, both wanting to reach a full octet, but they're going about it in different ways. The last one is delocalized. We'll get more into that one later. That's for a metal. And delocalized just means electrons have the ability to flow. Ionic bonding, a little more information about that. First of all, ionic bonding, there's a transfer of the electrons from a metal to a nonmetal. The cations are positive because they've lost, anions are negative because they've gained, and they become together positive negative attraction, what we call an electrostatic force. Now, drawing a Lewis dot formula for ions is going to be different than it is for our covalent compounds or molecules, and this is for the only time we're going to see this until the very end in preparation for the test. But for sodium has one valence electrons in column 1. And the sodium ion, as we write it out the same way we memorize it back with nomenclature, it's the Na+. Fluorine's in group 17, so it has 7 valence electrons. We show all 7 valence electrons. Its goals become like a noble gas, so fluoride is a F-, meaning that it actually has acquired a full octet, so we show it when we're drawing the Lewis dot formula here of an ion. Put brackets around it and a negative charge on the outside. That negative charge on the outside is just showing that we had to gain 1 electron to get there. The magnesium, again, is in group 2, has 2 valence electrons. Magnesium then wants to lose those 2, so for its ion state, we just say Mg2+. Oxygen is in group 16, it has 6 valence electrons. It wants to gain 2 more, so oxide is in 2-. So we get full octet, and a 2- means it had to gain the 2 electrons to get to its full octet. So that's how we write it out in the ion state. Now we can actually then come together and form out compounds. So let's go back in time. Let's go back to last unit. When we go back to last unit, we drew out the electron configuration for sodium and chlorine. We know that the valence electrons live in only 2 houses. That's the S and the P house, and they must be in the highest energy level, the same number. So my sodium is the highest number is 3. I have 1. The S has 1 valence electron. Makes sense because it's in column 1. Chlorine has again, I look over there, it has 2 in the S and 5 in the P. So it has 7. Makes sense because it's in column 17. What happens though in this process, sodium says, you know what, I want to lose, and chlorine says, I want to gain. So in the process, they actually transfer the electrons out. And now the transfer, this actually becomes a 6. And so now it has the appearance of a full octet. And this goes back in time, has again a full octet. It falls back into it. Of the appearance of an actual noble gas, which was your overall goal. Another way we can write it is sodium has 1 valence electron, chlorine has 7. Sodium says, you know what, I want to lose it. Chlorine says, I want to gain it, so they transfer it. How we can write this out is the Lewis dot formula for this ionic compound. Is we write it out this way. We write sodium, and next to it we write chloride. And the way we write chloride out with this full octet and a -1, it gained 1 to get its full octet. So that's why I write -1 because it gained 1 to get the 8. We know that there is no overlapping here. There are opposites. So we see a positive and negative attraction. That's the electrostatic force is actually holding them together. Doing the same thing for magnesium now. Magnesium, 2 valence electrons, has 2 it wants to give away. As 1 chlorine comes in and says, no, I'll take 1 of them. And the second chlorine comes in and says, I'll take another 1 of them. Now, we already know the formula because Mg is a 2+, and so I add Mg, and my chloride is a -1. So I already know that it's, again, 2+, and this chloride is a -1. So I already know the formula is MgCl, and I need 2 of them to zero it out. So again, here I go, MgCl and Cl, so it's MgCl2. So we already knew that formula. We're just taking a closer look at what's happening. So we have a transfer of electrons on both sides. We're going to write this out as a Lewis dot formula. I show my Mg2+, and I have a chloride on this side. It has gained a full octet, and the chloride on the other side has also formed a full octet. And so it actually looked like this. And this is again how we draw the Lewis structure for an anionic compound. We really won't, like I said, we won't see it except for this day. And then we'll go on, we're going to focus on the molecules, excuse me, and those are covalent compounds. Moving on, a little more information about the ionic compound before we stop and move on. Ionic compounds form a 3D crystal lattice. It's a 3D arrangement of positive and negative ions, and they form a solid. So it's positive, negative, positive, negative, positive, negative, and they come together and form this crystal lattice. We don't really find ionic compounds by themselves, so I don't find an individual NaCl, which is my sodium chloride or table salt. I don't see just one of those. What we'll see is billions of those actually joined together, forming an actual 3D crystal lattice. Lattice energy, this energy actually holding together, or energy absorbed by 1 mole of ionic solid. And this, they'll actually, then what they'll do to measure how much energy is holding together, they'll separate it. And so in this process, since it's absorbing energy, this is endothermic. Endothermic reaction. We get more into that later on. But what I do want to point out, lattice energies for ionic compounds are strong. Because they have large lattice energies, it means the ionic compounds themselves are strong. Because they themselves are strong, it means they have a high melting point. It takes a lot of energy to melt. To melt, you have to break bonds. So it takes a lot of energy to that. And also because it has a high melting point, that's why at room temperature we'll find them actually as solids. For example, table salt NaCl will not melt on your table. It will still remain as a crystal. Ionic compounds are generally soluble in water. The solutions conduct electricity well. They will not conduct electricity in the solid state though. But in liquid state, they have electrolytes. Electrons have the ability to flow and conduct electricity. Electrolytes are the same electrolytes we're talking about, like for sports drinks. So you have to be careful with sports drinks because there's a lot of salt in them. So make sure you're active when you're drinking those. The molten state is a liquid state. So if I take salt and I melt it into the liquid state, it also will be able to conduct electricity well because the electrons have the ability to flow. And this is a key thing. For something to conduct electricity, charged particles or ions must have the ability to flow or actually move.